Hello, good morning. Um, so today we're gonna cover the um rest of Coulomb's law. Oh, Yosh of the 777th Legion. Hello. Okay, let me just open this up. Okay, clear that. All right. Okie dokie. Let's get started. So we only have a couple of questions left, but before we start, let's just briefly go through what we know. Okay, we know that according to Coulomb's law, the electric force between 2 point charges is given as Q1, Q2 over 4 pi epsilon r squared. We know that the electric field strength E is given as Q over 4 pi epsilon r squared. We also know that the electric potential is Q over 4 pi epsilon r. We also know that the, what is this there? The electric potential energy is QQ over 4 pi epsilon r, right? And then we know that the... Bye, Yosh! Thanks for dropping by. And we also know that the negative of the electric field strength is equals to the potential gradient. And then we know that the resultant scalar, the resultant electric potential, you just add them up. Just add, okay. And then for resultant electric field strength, you have to take E1 and add it with the negative of E2. Usually in the exam, they only have 2 particles or 2 point charges. Okay. And then we also did a bunch of these graphs here. Hopefully you still remember how to interpret these graphs. Okay. All right. That's what we know so far. So let's continue with question 5. You have 2 small solid spheres A and B. Oh wait, I should also mention that the electric field strength R graph is given as, let's say this is R equals to R, then it goes like that, and then it goes like this. Okay, so when R is less than or equals to R, E is 0. And then for electric potential, it goes like that, and then stays flat like this. Okay? All right, going back here. Suggest why the electric field strength is in both spheres is 0. So we have kind of discussed this before. So let me show you the answer. So inside a sphere, doesn't matter whether it's solid or hollow, there would be no movement of charges. So the field strength would be 0. What is there to talk about? In electric field, charges would move, but because there's no movement of charges, therefore electric field strength must be 0. Yep, that's just 2 marks. Alternatively, you could say charges in the metal do not move, therefore no resultant force on charges, so no electric field. Because charges in metals only move if you have a current. It's a bit of a circular argument here, but the point is, if you put a charge inside a sphere, the resultant force would be 0. So it starts with this, and then because the resultant force is 0, therefore there is no electric field strength. So you can just go with this, and then you say this. I think that makes the most sense. Okay, so going back here. Show that the electric field strength is 0 at point P. Explain your working. So you need to show that the resultant electric field strength is 0 over here. And we can see that these charges, they're both positive. Okay, so what do we do? Well, talking about the charges in metal and calling it a circular argument. Pun not intended. Or is it not intended? Ho 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 ho. Okay. Where's my pen? This is my pen. Let's use rate. Okay. Where was I? So we want to find the resultant electric field strength at P. So we have to take the electric field strength due to A plus the negative of the electric field strength due to B. Okay, it doesn't matter whether the charges are like or unlike or positive or negative. This is always the formula that you use. So E, the first one is going to be, let's see. What is E again? E is actually electric field strength, which is Q over 4 pi epsilon r squared, right? So the first one is going to be 3 picocoulomb, 3 picocoulomb, yep, what am I saying? So 10 to the power minus 12. Is it too small? Can you actually see? Okay, so 3 times 10 to the power minus 12 over 4 pi epsilon. Epsilon is 8.85 times 10 to the power minus 12. And then r squared. R is going to be the distance from the point charge, which is assumed to be the center of the sphere, to P, which is 5 centimeters. So you put 5 times 10 to the power of minus 2. And then minus, what's this guy here? This guy is 12 times 10 to the power of minus 12. And the same thing. 4 pi epsilon. And then your R, oh wait, I forgot to square this one. R should be 15 minus 5, so that's 10. And then you square that. So hopefully that's going to give you 0. Now, let's put that into our calculator and see what that gives us. Okay, so on the left side we get 10.79. What about this guy on the right? Wait a minute. What? Why did I get something so bizarre? Hang on, let me just try that again. Oh, there we go. Hey, it's the same thing. Therefore, we get 0. Shown. Yep, that's it. That's all there is to it. Okay. Calculate the electric potential at P. So how do we find the electric potential at P? Remember, to find the resultant electric potential, you just have to add the electric potentials up, because electric potential is a scalar. So resultant electric potential is the electric potential at A plus electric potential at B. The electric potential is given as E over, and what am I even writing? Electric potential is Q over 4 pi epsilon R. Okay, so just add them up. I can actually factorize 1 over 4 pi epsilon. So we have Q over R plus Q over R. So this one is for A, this one is for B. Okay. So we have 3 picocoulombs. What is the radius? Not radius. What is the R? R is going to be 5 times 10 to the power minus 12, minus 2, sorry. Plus 12 picocoulombs divided by 15 times 10 to the power minus 2. Okay. Let's see. What do we have? Okay. Divide by 4. Divide by pi. Divide by 8.85 times 10 to the power of negative 12. We should get about 1.26 volts. And done. Oh, there's also something else I forgot to mention. So just go back here. Another kind of interesting relationship that you have to know is between V and U. Because sometimes you can use this in the exam as a bit of a shortcut. So how is V and U related? Well, you can see that U is actually V times Q, right? So this is also a pretty useful equation to know. Kind of similar to how U is V times Q. Well, U is equals to gravitational potential times M. Right, it's kind of similar to this one. Okay, just thought I'll mention that before I forget. Okay, come back here. Okay, so we found our electric potential. Then for part D, a silver nucleus has speed v when it is a long distance from point P. Use your answer in C to calculate the minimum value of speed v such that the nucleus can reach P. Okay. So, when it says a long distance from P, that means it is at infinity. It is super far away. So how long does it take? Not how long. What is the minimum speed the nucleus must have in order for it to go from infinity to P? So that is essentially what they're asking you. Okay. Well, you can see that the nucleus, because they mentioned the nucleus, that means it has no electrons, which means it is positively charged. And you're moving it towards a region with positive electric potential, right? Because these two things are positive as well. So you're going to have to put in work to move the nucleus towards this region because they repel each other, right? Therefore, you need to have some minimum speed if you want to reach point P. Okay? So because the nucleus is going to slow down as it gets closer and closer to P because there is a repulsive force. So how fast does the nucleus have to be going in order to reach P? So it stops at P. So this is actually a conservation of energy kind of question because the acceleration, the resultant acceleration varies, right? Because the force depends on the distance between the point P and the nucleus. So if your acceleration changes all the time, you have to use the conservation of energy method, basically the master equation. You can't use kinematics. So what you want to do is you use the master equation, but there's no air resistance, you can ignore that. There's no external force, so you ignore that. So eventually you just end up with the change in kinetic energy is equals to negative of the change of the potential energy, right? So kinetic energy is going to be half m v squared minus half m u squared. V is going to be 0 because it's going to stop at P. U is what we are trying to find. And then for electric potential energy, you have to use this expression here. Q1, Q2 over 4 pi epsilon r. So one of the Q's here is going to refer to the charge of P. Not P, sorry. Charge of the nucleus. Okay, which is going to be, positive 47 E. What about the other Q? The other Q refers to the Okay, so the other Q refers to the average collective charge at point P, but point P doesn't actually have a charge, right? So instead of using this, what we want to do is we want to use U equals to VQ. So Q is going to be the charge of the nucleus, but V is going to be the electric potential at that point. So we should use this equation instead of this one, because we don't know what the collective average charge is at point P. Okay, but we do know what the resultant electric potential is at point P. Okay, so if I have a change in the electric potential, then the change would affect my electric potential as well. But my charge is a constant, so we can just put the charge outside of the change. So essentially this is going to give us change in V times Q. Okay, so what is the change in V? Well, the change in V is final V minus initial V, so that's going to give us final V minus initial V times Q. So what is my final V? My final V is the resultant electric potential that we got earlier, which was this one, 1.26. So I'm going to put that in. My initial electric potential is going to be 0, because remember, at infinity, electric potential is defined to be 0. That's just by convention, that's what it's defined as. And then Q is going to be the charge of my silver, which is 47 times 1.6 times 10 to the power of negative 19. Okay, and then actually, you know what? Let me just leave this as Q for now. Don't keep writing that. Okay, so we end up with 1.26, and then I move the negative over, so the negative disappears. There's a q here. So u is going to be 2 times 1.26, which is 2.52 q, and then divide by the mass of the nucleus, and then I square root that, and I retain the positive square root. Because, well, it actually doesn't really matter. And then let's say we're going to put in our values now. So 1.6 times 10 to the power negative 19 over the mass of my nucleus, which is 107, times the unified atomic mass, which is 1.66, times 10 to the power negative 27. And the whole thing is square rooted. So what do we get? Boop, 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 boop. We get 1,507 meters per second. So it has to travel at almost 5 times the speed of sound in order to reach point P. There you go. Done. Okay. Okie dokie. Yeah. Are you guys okay with this? All good? Alright, moving on. A small charged metal sphere is situated in an earth metal box. The figure below illustrates the electric field between the sphere and the metal box. Okay. By reference to the figure above, state and explain whether the sphere is positively or negatively charged. So, by looking at the electric field lines, what do you think the charge on the metal sphere is? Positive or negative? What do you think? You should know this, actually. This is actually from AS. What? You guys don't know what the charge of the sphere is? Oh no. I'm disappointed. It's positive, right? Positive charges emit electric field lines, sort of go out like that. It's positive because field lines radiate outwards. Why does it appear as if the charge on the sphere is concentrated at the center of the sphere? So, why does it appear so? The reason has to do with the fact that a sphere is, circular. So if you look at the few lines here and you try to extrapolate the lines, they would appear as though they are originating from the center. So it seems as though the charge is a point charge located in the center of the sphere. And another reason you could talk about is the fact that these few lines exit the surface of the sphere at an angle of 90 degrees. So they exit perpendicular to the sphere, which contributes to, the illusion that the charge originates from the center. So that's one thing you could say. So let me just scroll down. Okay. So you say all lines appear to radiate from the center, or you can say all lines are normal to the surface of the sphere. Right, so one of those two things. Okay, part B. On the figure above, draw an arrow to show the direction of the force on a stationary electron situated at A. So if I have a stationary electron here, in which direction is this A going to experience a force at? So remember, electrons are negatively charged, so they should experience a force towards the positively charged sphere, and it should be like this. So the force should be tangent to that point, not pointing towards the center. Okay, so that's a very common mistake that people make. They draw the force such that it points towards the center, but it doesn't have to point towards the center. You just have to draw it so that it is tangent at that point. Okay? Because if you draw it to the center, it's not going to be tangent anymore. It's going to intersect more than 2 points. Okay, so next up, the radius of the sphere is 2.4. The magnitude of the charge Q on the sphere is 0.76 nanocoulombs. Use the expression blah blah blah. Calculate a magnitude of the potential at the surface of the sphere. So nothing to it. You just sub in your values and get your answer. Easy peasy. Okay. And put that in my calculator. Oops. And then we get 285 volts. Done. Okay, state the sign of the charge induced on the inside of the metal box, hence explain whether the actual magnitude of the potential will be greater or smaller than the value calculated in 1. So I'm just going to briefly draw the metal box here. So you can see that this is the positive charge, right? So the magnitude that we calculated earlier is the potential at the surface of the sphere. Okay, so is the actual magnitude of the potential going to be higher or lower than 285? What do you think? And why? This is a metal box, by the way, which is important. Because metal box, a metal surface, or a metallic object would allow, well, if you put a metallic object in the influence of an electric field, you're going to see charges move. All right. So what's happening here is that because you have an electric field going through the metal box, so the molecules in the metal box would have the electrons closer to the center of the box, so the inside of the box would be negatively charged, slightly negatively charged, and the outside of the box would be slightly positively charged. Okay, which means the resultant magnitude at the surface of the box, the resultant electric potential at the surface of the box is going to be slightly lower than what you just calculated here. Because what you've calculated here is only the electric potential due to the sphere. But you have not included the electric potential due to the negative and the positive charges here. Okay, so the negative charges are going to contribute a bit more than the positive charges. because they're closer to this point over here. Because remember, the electric potential is Q over 4 pi epsilon r. So V is inversely proportional to R. So the smaller R is, the greater the contribution to V is going to be. Okay, so what you want to say is, where is it? Negative charge is induced inside of the box. The formula applies only to isolated point charges. Basically, the formula only applies to the charge in the sphere. And then, so less work done moving test charge from infinity. So basically, it tells you that the electric potential will be lower because you need less work to move it from infinity to that point. Remember, the test charge is always going to be positive. So work must be done moving a test charge from infinity to the positive sphere, because you're putting two things that are like charges together, so they would repel each other. So you need to put in work. But if you have a negative charge in the vicinity, then less work needs to be done. Okay, so potential is lower. So these are the things you want to say. Okay, hopefully that makes sense. Okay, part D. A lead sphere is placed in the lead box in the free space in a similar arrangement. Explain why it is not possible for the gravitational field to have a similar shape to that of the electric field. So if you look at the diagram here, you can see that the electric field sort of bends a little so that it is normal to the surface of the box. See, they're all normal to the surface of the box. And the reason it is normal to the surface of the box is because there are charges induced on the surface of the box. So remember, a negative charge would have an electric field drawn like this, right? We did this in AS. So if you have a negative charge on the surface of the box over here, then the electric field lines would enter normally as well. They come in perpendicular to the surface. That's why they sort of bend a little here. Okay? But if you replace this with a lead sphere in a lead box, it's not going to bend anymore. And the reason for that is because let me just show it to you. Because the gravitational field is always attractive. So the field lines must be directed towards both the box and the sphere. Okay, but for the diagram that we just did, one is negative, one is positive, so the field lines go from the center to the box. But for a gravitational field, both the lead sphere and the lead box, they have masses, which means they are attractive. So the field lines should be going to the box and the sphere. Okay. So I think we have one last question. So helium contains 2 protons. In the model of a helium nucleus, each proton is considered to be a charged point mass. The separation of these point masses is assumed to be this guy here. For the 2 protons, calculate the electrostatic force. Okay, so the force between 2 charges, you just use Coulomb's law here. F equals to QQ over 4 pi epsilon r squared. So each proton means the charge would be 1.6 times 10 to the power negative 19, and then square because there's 2 of them. And then 4 pi epsilon R is 2 times 10 to the power negative 15 squared. No, wait, actually, let me send a quick message. Okay, so let's put that into our calculator. Two times 10 to the power minus 15 squared. So that's 57.5 newtons. And as you can see, that is a crazy huge force between two protons. Considering the protons are so small and the masses are so tiny. But the electrostatic force, the force of repulsion between the two protons, is so huge, right? And what about the gravitational force between the two protons? Right, gravitational force, we have to use gmm of r squared. Okay, so g is 6.67 times 10 to the power negative 11. M is going to be the mass of a proton, so 1.66 times 10 to the power negative 27 squared, because there's two of them. R is going to be the distance between them, which was 2 times 10 to the power minus 15 squared. Okay, so what did we get? Oops, hang on. You get 4.59 times 10 to the power negative 35 newtons. Okay, so if you have two protons in a helium atom, so they're very close to each other because they are in the nucleus, right? So two protons in the nucleus, the repulsive force is 57.5 newtons, and the attractive force is only a pathetic 4.59 times 10 to the power negative 35 newtons. So how is it that the protons stay together in the nucleus? It doesn't make any sense, right? Unless there is some other force that is very strong holding them together, aka the strong force. Okay, that's why you have the strong force holding the protons together in the nucleus. So, suggest why there must be some other force between protons in the nucleus. So you just say that the repulsive force, the repulsive electrostatic force is much greater than the attractive gravitational force. Therefore, there must be a much stronger attractive force holding the protons together in the nucleus. There we go. Okay, so part 2. This additional force must have a short range. Alright, so if you remember when we did strong forces in AS, they must always have the strong force has a very short range. And why does it have a short range? Because if it has an infinite range like gravitational force and electrostatic force, then it's going to overcome all the forces in the universe, and instead of what we have now, we're just going to exist as a gigantic nucleus because everything's going to be pulled together, right? So outside the nucleus, there is a repulsion between protons. If it's not a short range, all the nuclei would stick together and we would have a gigantic nucleus. So essentially that's what you want to say. Attractive force must act only in nucleus. Okay, so that's it. Okay, so we are done with Coulomb's law. So all that's left is capacitance, the new chapter, cosmology, medical imaging, electronics. They've actually taken out of the syllabus, so you guys are very fortunate because that is usually the chapter that people find most difficult, so that is gone now. But you also have a new chapter in AS called polarization, which is going to be assumed knowledge when you go to A2. Okay, so Mr. Zigri would cover that. Yes, the most fun chapter. Oh, the most fun chapter, electronics. Yeah, well, most people find it the most difficult, but I've also known people who find it interesting, who found it interesting. What other chapters do we have left? We also have alternating currents, magnetic fields, electromagnetic induction, quantum physics, also very interesting. Nuclear physics, that's still in the syllabus. Communications, I think they've taken that out already, so that's gone. So we have 1, 2, 3, 4, 5, 6, 7, 8 chapters left. 9 chapters left. It's difficult but also fun. You are not wrong. You are not wrong. There we go. So, Mr. Zikri will take over the class in September, and he will continue with the rest with you guys. Okay. So it's been a pleasure teaching you guys. Though it's kind of unfortunate that we don't get to say goodbye in person. But regardless, it's been fun, and all the best to you guys. Okay. And yep, I don't know what else to say. I'm not very good with farewells. But yeah, keep in touch, and maybe I'll see you again at some point. Who knows? Yep. Goodbye.